Hi, this is Constantin Bilz from the University of Birmingham with a talk on large sets without Fourier restriction theorems. This is part of the Fourier Restriction Online 2021 workshop, and I would like to thank the organizers for inviting me. Every set in Euclidean space has a Hausdorff dimension associated to it, which gives us a notion of its size, and the set may also have some Fourier restriction theorems. The goal of this talk is to show that these two quantities, these two properties of a set, Hausdorff dimension and Fourier restriction theorems, are mostly independent from each other, except for a well-known inequality constraint that always holds. This is motivated by the recent emergence of maximal restriction theory, which we will talk about. You also use some results from fractal restriction theory, that is, restriction to fractals, which we will then complement with a construction of a counterset that is large and has no Fourier restriction theorems that are non-trivial. So let's start by taking an abstract view on restriction theory. In the widest possible sense, the restriction problem makes sense for all exponents p between 1 and 2, q between 1 and infinity, and any Fourier measure mu on Rd. We then say that a bounded linear operator R mu from Lp of Rd equipped with Lebesgue measure to Lq of Rd equipped with mu is a restriction operator if for any function f that is both integrable and in Lp we have that R mu f is equal to f hat mu almost everywhere. First of all, this condition makes sense because for an integrable function its Fourier transform is defined at every point. So in particular we can talk about values mu almost everywhere. Of course, the main way to obtain a restriction operator is by proving a restriction inequality on some dense subset of Lp. That's how we usually do it. So here are the trivial examples. At the one endpoint, if p is equal to 1 and q equal to infinity, then any Fourier measure mu works. We have Fourier restriction for any Fourier measure in that case. At the other endpoint, if p and q are both equal to 2 and mu is the Lebesgue measure, then the Fourier restriction problem is really just Plancheret's theorem. In this language, Stein's observation in 1967 was that non-trivial restriction operators exist. Namely, when the exponent p is strictly between 1 and 2 and mu is a singular measure. Of course, this strongly depends on properties of both the measure mu and its support. In particular, if mu is a typical measure supported in a submanifold, then curvedness of the submanifold will play a key role. Similarly, if mu is a fractal measure, then there is an analogous key property that is usually called pseudo-randomness. So we have to find restriction operators via this property that R mu f is equal to f hat mu almost everywhere for every function that is both integrable and in Lp. Or in other words, R mu f is equal to f hat as functions in Lq of mu. So in 2019, Müller, Ricci and Wright asked the rather natural question whether there continues to be some kind of intrinsic pointwise relationship between R mu f and f hat if we only assume that f lies in Lp and not assume that it is integrable. So let's first see what the restriction inequality implies. For this, take an averaging kernel chi, which is integrable and bounded. It has integral 1, and we let chi r be its one dilation. Then we have that the Fourier transform f hat convolved with chi r is equal to the restriction operator applied to f times chi r check. That's because f chi r check is both integrable and in Lp. Furthermore, if we take the limit as r goes to 0, this will converge to R mu f because the restriction operator is bounded. This convergence takes place in Lq of mu, and in particular it implies that we have pointwise convergence mu almost everywhere along some sequence of radii rk that go to 0. Here we want to do better, we want to strengthen the mode of convergence. So we will strengthen the mode of convergence by essentially, instead of using the restriction inequality, using a stronger inequality that implies restriction. And the mode of convergence we're interested in is related to Lebesgue points. Just to recall, we call a point psi a Lebesgue point of the Fourier transform I've had if there exists a value c such that the convolution of modulus f hat minus c convolved with chi r converges to 0 at psi as r goes to 0. And in this situation, c is called the regularized value of f hat at psi. Usually when we want to show the abundance of Lebesgue points in harmonic analysis, we use some kind of maximal inequality or perhaps variational inequality. And this is no exception. So Villarici and Wright also observed this lemma in their 2019 paper, namely if we assume this positive maximum restriction inequality that is written on this slide, then for mu almost every point in Rd, this is a Lebesgue point of the Fourier transform, and the regularized value corresponds to what the restriction operator gives at that point. What is the positive maximum restriction inequality? Well, it's basically the restriction inequality, but on the left-hand side, instead of f hat in the norm, we have the supremum over our positive radii of the modulus of f hat convolved with chi r. So let's look at some other inequalities of this sort. The first one on this slide is just the same as the last slide, the positive maximum restriction inequality that we saw before. You might want to compare this to an oscillatory maximum restriction inequality, which is the second display on this slide. The only difference is that the modulus is now outside of the convolution rather than inside. So this will give you a slightly weaker inequality now. Both of these, the positive and the oscillatory version, can be regarded as inequalities from Lp to Lq of L infinity, because we take this L infinity norm over the radii here via the supremum. You could replace this L infinity norm in R by a variation norm, let's say a rho variation for some exponent rho. This would be a stronger inequality. You will get a stronger positive and a stronger oscillatory inequality. So here's a diagram of all those restriction properties. On the left-hand side, you can see the oscillatory inequalities. In the middle, there are the positive inequalities, and at the bottom, there is usual restriction. And at the right-hand side, there are pointwise convergence results. So we've seen that the positive maximum restriction inequality implies Lebesgue points mu almost everywhere. And before that, we've seen that the restriction inequality itself already implies convergence mu almost everywhere along a sequence for the Fourier transform. What we really want to have is an implication from restriction up to Lebesgue points mu almost everywhere. We would like to prove that if a restriction theorem holds, then we can somehow recover the restriction operator from the Fourier transform by taking local averages. We would like to have an implication from restriction to Lebesgue points. At the moment there's no implication in that direction, so I will have to draw some additional arrows in my diagram. The first arrow we can relatively easily draw is one from oscillatory maximal to positive maximal. This is something that Müller, Ricci and Wright again observed in their paper. You can prove this via some reflection trick. The key point here is that if you have an oscillatory maximal inequality with exponent p and q, then you only get a positive maximal inequality where p is replaced by 2p over p plus 1 and q is replaced by 2q. I'm still not done. There's still not an implication from restriction to Lebesgue points, so we need another arrow. And this one may look a bit magical. It is an implication from restriction to oscillatory variational restriction. And this holds whenever you have a restriction inequality from Lp to Rq mu, and Q is strictly larger than P, then you get an oscillatory variational restriction inequality with the same exponent and with the variational exponent rho larger than P. So this is a result due to Kovac in 2019. Here the arrow is restated as a theorem here. Just to repeat, it says that when Q is larger than P and LP to LQ mu restriction holds, then oscillatory LP to LQ variation norm with exponent rho of mu variational restriction holds for any rho larger than P. So this is really a maximal restriction principle, or if you want a variational restriction principle, because this works for any measure mu, there's no restriction. As a corollary, if we look back at the diagram, there now is a path from restriction to Lebesgue points via oscillatory variational restriction, oscillatory maximal, positive maximal, then Lebesgue points. And if you follow these arrows, you get now a corollary from Kovac's theorem, which is if you have a finite Breuer measure and you have LP to LQ mu restriction for some exponents P and Q, where Q is strictly larger than P, then if I take a function f in L2P over P plus 1, mu almost every point of the Fourier transform I've had will be a Lebesgue point, and the regularized value will correspond to the restriction operator at that point. So this already gives a very good answer to the question that Müller, Ricci and Wright asked, namely whether restriction implies Lebesgue points, in other words, whether restriction implies intrinsic restriction. Of course, there are some inefficiencies here. For example, we still have this assumption Q larger than P in the theorem, and we have that, well, F can only be in 2P over P plus 1 here rather than in LP. But this will be good enough for our purposes. So let's move on to the next topic, which is Fourier restriction to fractals. The point I want to make is that Fourier restriction is not something that is unique to manifolds in any way. Around 2000, Mockenhaupt and Miesisch both independently from each other observed that the standard classical Thomas Stein argument that proves restriction can also be used for much more general class of measures than was originally thought. The key assumption of that argument is really that the measure that you're looking at has some Fourier decay. And this leads to the following theorem, where Backenseger in 2011 provided the endpoint. If you have a finite Breuer measure mu and you have some exponent beta between 0 and d, such that the Fourier transform mu hat decays at a rate at least xi to the power minus beta half as xi goes to infinity, then you get an LP to L2 mu restriction inequality for a certain range of exponents p from 1 to 4d over 4d minus beta. Of course, this gets better as the decay of the Fourier transform gets better. You can now also look at the supremum of all possible values of beta for which this decay property 1 holds. And this supremum is called the Fourier dimension of the measure. So in these terms, qualitatively what the theorem says is if you have a measure of positive Fourier dimension, then you get some kind of non-trivial restriction theorem. And this tells us that there are many examples of Fourier restriction theorems on many different kinds of measures, namely whenever the Fourier dimension is positive. So here's a list of sets that support measures of positive Fourier dimension. Of course, first in that list are curved submanifolds that we know very well in harmonic analysis. But then there's also a very long list of pseudorandom fractals that do this. So there are a couple of classical examples, such as when you take a set and take its image under some kind of random process, such as Brownian motion, what you typically get is a set that supports a measure of high Fourier dimension. There are examples from Diophantine approximation. For example, if you look at sets of well approximable numbers, natural measures on those sets do have Fourier decay, so have positive Fourier dimension. Also classically, the last point on the slide, there are various constructions based on countersets that have various properties with regards to Fourier dimension. And a more recent topic is also limit sets of certain nonlinear group actions can have positive Fourier decay. It also makes sense for a given set to ask what is the best possible restriction exponent that you can get for measures supported in the set. And that's what I will call the endpoint restriction exponent, Pres of E. So it's defined as Pres of E is the supremum of the set of all exponents P between 1 and 2, for which Lp to Lq mu restriction holds for some Borel measure mu with mu E larger than 0, and some exponent Q between 1 and infinity. Of course, the trivial L1 to L infinity mu bound implies that Pres of E is always at least 1. On the other hand, P equal 2 is clearly the largest possible endpoint restriction exponent you get, and that occurs, for example, if E is a set of positive Lebesgue measure, then by Plancheret's theorem, Pres of E is indeed equal to 2. For a typical set, the endpoint restriction exponent will be strictly between 1 and 2. So it's reasonable to ask whether there's any kind of relationship between the restriction exponent and the size of the set, for example, the Hausdorff dimension of the set. And the answer to that is yes, there's an inequality saying that the endpoint restriction exponent of E is always at most 2d over 2d minus Hausdorff dimension of E. This is a consequence of Frostman's lemma. And also this inequality is optimal, as Waber and Wang in 2017 showed. Whenever you take a number alpha between 0 and d, then there exists a compact set E in Rd that has Hausdorff dimension alpha, and for which the endpoint restriction exponent is precisely this 2d over 2d minus alpha, showing that the inequality above is optimal. How did they prove it? They used some kind of counterset construction. So the question left open by this is really, are there any further relationships between Pres of E and the Hausdorff dimension of E? We've seen this inequality now, but is there an inequality the other direction, or are there any other numerical restriction between those two quantities? So that's really the purpose of this talk, to answer this question. And this is why our own counterset construction will come in. So let me start by showing you this main theorem, claiming that we can find a function in the intersection of all Lp spaces for p strictly larger than 1, whose Fourier transform has no Lebesgue points in some compact set of full Hausdorff dimension D. So this is one function in all Lp spaces for p larger than 1. In other words, for the Fourier transform of this function, the set of non-Lebesgue points has full Hausdorff dimension. This theorem is optimal in two ways. First, because you can't extend it to the closed range from p equal 1 to p equal infinity, because at p equal 1, the Fourier transform of an L1 function is continuous, so it does have Lebesgue points everywhere. So the conclusion of the theorem is clearly impossible. On the other hand, by the Lebesgue differentiation theorem, we know that Lebesgue almost every point of the Fourier transform should be a Lebesgue point. So we can't make the non-Lebesgue set to have positive Lebesgue measures, say. In that sense, full Hausdorff dimension D is the best we can do. We can't have positive D-dimensional measure. So what does the theorem imply? We can combine the theorem with Kovács's result that we discussed earlier, the maximal restriction principle, which essentially told us If we have restriction, then we have maximal or variational restriction, and this implies that we have Lebesgue points for Fourier transforms. And our theorem said something about the Fourier transform of a certain function not having Lebesgue points. So if you put those two together, you get a corollary like this, saying that there exists a set in E and RD, again of full Hausdorff dimension. It will be the same set as in the last theorem, such that LP to LQ mu restriction fails whenever mu is a measure that assigns positive measure to E, and P and Q are any exponents except that P is not allowed to be equal to 1. So basically, this is a full dimensional set for which any non-trivial restriction inequalities fail. In particular, this set avoids any measures that have restriction theorems. It avoids all those curved submanifolds and all those pseudo-random fractals. And now we can combine this corollary with the result of Weber and Wang that we saw before. We have a corollary that tells us there's a set that has very few restriction inequalities, and their result was they can find a set that has very many restriction inequalities. And by an argument that combines these two, you get the following corollary saying that, again, if we pick any dimension alpha between 0 and d and any exponent in the same range we saw before from 1 to 2d over 2d minus alpha, then there exists a compact set E that has dimension alpha and where the endpoint restriction exponent is exactly equal p. So this answers our earlier question about whether there could be any further relationships between Hausdorff dimension and endpoint restriction exponent. The answer here is no, there can't be any other relations between those two numbers. So let me try to give you an idea about the proof of our main theorem. We use a counterset construction for the proof, so let's start with the easiest counterset available, which is the 1/3 counterset on the real line. So what you do is you start with an interval on the real line, and you start by removing the middle third of that interval, so that you get two remaining intervals of 1/3 the size on the left and on the right, and then you remove the middle third from each one of those to get 4 remaining intervals. From the 4 remaining intervals, you remove the middle third from each one, and so on. The remaining white set that you get is the 1/3 counterset, and it is the non-Lebesgue set of a certain function g that I sketched here. And the function g basically assigns positive weight 1 to all the removed intervals at generation 1, and it assigns weight -1 to all the removed intervals at generation 2 and all the other even generations. So odd generations get a positive weight, even generations a negative weight, and this is what g does. Then as you take averages over the whole interval, you will see that this is a certain number. The average of g over the whole interval is a certain positive number. And if you take the average over one of the remaining 1/3 intervals on the left or right, you get the same average, but now it has a negative sign. And as you keep zooming into smaller and smaller remaining intervals, these averages will oscillate between the same two values. One is positive, one is negative. So in particular, this shows that the points in the remaining white set are non-Lebesgue points of this function. So this already does some of what the theorem promises. We have a set that is a non-Lebesgue set of a certain function. But the theorem claims a lot more, namely we wanted to have this set to be full dimensional, which we don't have. This 1/3 counterset has a dimension that is smaller than 1. And also the theorem wanted the now inverse Fourier transform of G to lie in all those RP spaces for P larger than 1, which is not true here. The inverse Fourier transform is hardly in any RP spaces in this case. So we need to improve our construction. The idea for this is we now want to, instead of removing the middle third from each remaining interval, we want to remove smaller and smaller proportions from remaining intervals so that the counterset we get starts to look a lot more like the interval. In fact, if you do this, if you remove less at each generation, you will increase the Hausdorff dimension of your set. The only thing we need to pay some attention to is, while if we remove too little at every generation, then our oscillation of averages that we got before for the function g may be destroyed, because all the averages may go to 0. So what we do is very occasionally we remove relatively large intervals from the remaining intervals. So at very occasionally we pick a generation or two at which we remove large intervals rather than small intervals. So in this way we can have both. We can have a large Hausdorff dimension of the remaining set and still preserve this oscillation of averages. The thing that remains is to show that the inverse Fourier transform T check lies in all those RP spaces. And here we will make use of the fact that the Fourier transform of an indicator of an interval already lies in those RP spaces, and we want to sort of compare these two things, the inverse Fourier transform of G and the inverse Fourier transform of the indicator of the interval. If you normalize the interval appropriately, then the Fourier transform of the indicator of the interval is the sinc function sin psi of xi, and this can be written as an infinite product of cosines, like so. This can be proved, for example, using some telescoping argument where the double angle formula plays a key role. You can also truncate this infinite product after finitely many terms, namely logarithmically in psi many terms, so that you get this product that is a product of finitely many terms for every psi, and this product decays at a very good rate, namely at a rate psi to the -1, so it lies in all RP spaces. P is larger than 1. We have on the real line here. So our Counterset is constructed from a sequence of dissection ratios. The dissection ratios are related to how much we remove from the remaining intervals. If a dissection ratio at some generation is very close to 1/2, then that means that we remove very little from the remaining intervals. If the dissection ratio is close to 0, then we remove a lot. So in general, we would like the dissection ratios to be close to 1/2, but sometimes they will be closer to 0, as we discussed before. So now you can take this inverse Fourier transform of the function g that we saw before, take its RP norm, and you will find that some of the key terms in that integral norm are these products of cosines in 3 here, which are essentially a little bit like the products of cosines in 2, but instead of multiplying by 1/2 at every step, we multiply by a dissection ratio at every step. So this is 1/2 times dissection ratio at generation 0 times dissection ratio at generation 1, and so on. So we said that we wanted most of those dissection ratios to be close to 1/2, which would make this look a bit more like 2. But we wanted some of the dissection ratios to be far away from 1/2. So what we do for those is we pick negative powers of 2. So like 1/4, 1/8, and so on. In this way, where we don't get exactly the same as in the product 2, but rather the effect of this is that we jump over some terms in the product in 2. So basically, if we do this kind of assignment of dissection ratios, what we get is that 3 will look like a perturbed version of 2, where there are also gaps. Some terms are missing. So we need some estimate for perturbed versions of 2 with gaps, which is in the paper. To conclude, there are 2 key points I want to highlight. First, our main theorem says that Fourier transforms of RP functions can have large non-Lebesgue sets when P is strictly larger than 1. The second point is, combining this with some results in maximal and fractal restriction theory, we can show a rigorous statement saying that Hausdorff dimension and Fourier restriction theorems are really mostly independent properties of a set, except for this one inequality that came out of Frostman's lemma. One open question that comes out of all of this is, can we perhaps say more about these Lebesgue sets or non-Lebesgue sets of functions that are Fourier transforms of RP functions? We saw that Lebesgue differentiation gives some necessary conditions on those sets, and also restriction theorems via maximal restriction give some necessary conditions on those sets of Lebesgue points. But are these necessary conditions also sufficient? That I don't know, and I think it would be an interesting question. Thanks for listening.